Vamos estar aqui à frente, não?
Sim.
Você está para usar uma luta final. Porque eu costumo disponibilizar, né? Depois de dentro da pepita. Nossa, salada já é mais gostoso que o habitual.
Mas você tem que ir, quanto mais centralizado o cenário, quanto mais visualizado, chega a 10%. É diferente, né?
Você fez aí. Passar uma. Sei lá, nossa parte de postar no nosso Ai, mano, vai entender essas coisas. Nossa,
¿Esto está reservado o ya para la noche? No, para coger la noche. Si trabajo en Argentina es algo que viaje.
Porque bueno, ya viniste a la página.
No, solo había estado en Río y en...
Solo. Una ciudad buenísima.
En Río y Bucios, claro. Sí, fue lindo.
Rio e Rússia?
No, Bucios.
Búzios.
Acá en Brasil.
Dizem Russia?
No, I've been in Suriname.
Yes? Where part?
Yeah, I've been in Suriname. We have one project. That's a weird country. They're polymer everywhere. They're injecting polymer everywhere.
Yeah, I love polymer. I
can tell.
Yeah.
La voy a presentar ya.
Dale. Yo me voy a poner un cronómetro.
Hoje tinha disposição, né, velho? Já tem que
Boa tarde, pessoal. Vamos dar começo à última palestra do dia. Agora aqui temos a representante de uma de nossas patrocinadoras, que é a SNF Water Science. Ela é Ailén de Vita, engenheira química formada pela Universidade Tecnológica Nacional, atua como profissional na indústria de petróleo e gás há mais de 4 anos. Sua primeira abordagem à indústria de oil and gas foi em 2019 como assistente de laboratório de petrofísica e mecânica de fluidos na InLab SA. Atualmente, ela é engenheira de suporte técnico do laboratório e campo na SNF Argentina, onde participa do suporte integral a projetos de implementação de polímeros na Argentina e Sul-América, principalmente na área de recuperação avançada de petróleo. Além disso, dentro da equipe de suporte, destaca-se como referência em atividades de treinamento técnico, principalmente na área de recuperação melhorada. Por favor.
Hello. Can you hear me? Okay. So good evening to everyone. I'll have to switch to English because not Portuguese so far. I'll try to speak slow just for everyone to understand, but if you have any doubt, we have 30 minutes for questions, so feel free to ask when I'm finished, or to interrupt if you have any questions. Okay? So, okay. So today we're going to talk about EOR. Maybe some of you are familiar with the concept, maybe not. I'll try to explain everything from the basis. We're going to talk about EOR, chemical EOR implementation in Argentina. We're going to see some study cases, and also how polymer flooding, which is EOR, chemical EOR, that we're going to talk about, what's its role in energy transition. Okay, by energy transition we mean this switch from hydrocarbon as an energy source to renewable energy source, right? So this is an agenda for today's presentation. We're gonna be seeing an introduction on EOR, what it is, what we specialize in as SNF Argentina. Also, we're gonna see what kind of products we use in EOR and how we implement them at the oil field. Some examples of Argentina, as I mentioned, and also the EOR polymer flooding role in our energy transition, in current world energy transition. So, you hear me well? I think that's better. So for those who don't know, I think everyone knows what a reservoir is, but just in case, yeah, that's it. So to find a reservoir, we need to have a certain group of elements together. First one is a mother rock, or a source rock where the oil is generated. So after years and pressure and heat, we have oil formation, oil and gas. And then that oil migrates to a reservoir rock, which is a rock that has enough porosity and permeability to keep that oil there. This happens along millions of years, as you already know. And then we have a seal rock, which doesn't let the oil to build up to the surface. Okay, so if we didn't have this seal rock, we would have oil sometimes in the surface. So having these three main elements, we would have this fluid distribution like this because of density. We will have water and then oil and then gas. Okay. We have to understand in oil and gas industry that oil is not like a pool of fluids. It's more like a sponge with many fluids in there, and we are taking fluids from that sponge. It's not like a pool and we take a syringe and we take it off. So that's the first concept I want you to visualize, because we are having an advanced, we're gonna go deep in an advanced way of oil recovery. It's not the regular one. So just for you to visualize what that oil exploitation looks like, it's something like this. We have a layer, let's say the reservoir layer in the soil, and we have injection wells where we inject fluids, and then we have production wells where we extract fluids. And we will not only extract oil, we will also extract water and gas. Okay, so this is a very important concept, because we will see that how much water we produce is very important. Okay, so quick summary on stages of oil recovery. First one is primary, which is oil recovery through the own reservoir energy. I mean, if the reservoir has higher pressure than the atmospheric pressure, then we will lift it naturally, okay? So it will go to the surface naturally. Also, we can have secondary recovery, which can be skipped and go straight to tertiary or EOR, but it's recommended to at least produce a bit by secondary recovery. Why is that? Well, secondary recovery is mainly trying to keep the reservoir pressure with water or gas injection. It's pretty much what we've seen here. We inject water, for example, and then we push the oil, and we produce a mix of fluids, okay? Why it's important to inject water as well in the reservoir? Because we can understand how our reservoir behaves, and how much fluids our layer admits, how our layers are connected, how our wells are connected. So it's a very important stage. And then we move to EOR or tertiary. You may have heard both. EOR stands for enhanced oil recovery, which is when we try to go deeper, because secondary is not enough, or it's not cost effective, or we want to produce more oil, or we want to decrease water cut because we're producing too much water and we need to improve our percentage of oil. So we have many ways of tertiary recovery, not just one. We have a gas injection. You may have heard of carbon dioxide injection. Thermal, which is very used when we have very viscous oil, because it increases its temperature, so it lowers the viscosity. So lower viscosity, it's easier to move. And then we have chemical and other kind of tertiary recoveries. We are going to focus on chemical, which is mainly polymer flooding. You are going to see PF many times. It means the polymer flooding or polymer injection. And when I say water flooding, I mean secondary recovery. Okay. So we can also have surfactant polymer or alkaline surfactant polymers, but those are more advanced ways of tertiary recovery. We're going to focus on polymer flooding. So chemical EOR with polymer flooding is nothing but a viscous water flood. So I'm not injecting a high percentage of polymer. I'm going to show you right now what polymer is and how it looks like. But it's nothing but a water flood, more viscous. Okay. So basically we have this polymer that dissolves in water and increases its viscosity. And we have a very interesting effect. I mean, you're going to ask, all right, so why do I switch to polymer? I could inject just water. Well, look on how the water flooding looks like and how polymer flooding looks like. Polymer flooding reaches more surface with the same flow rate. So we can get through more oral space, and we can therefore get more oil in our production wells. Okay, why is that? Why does this happen? Well, because we have this factor which is mobility ratio, which is basically the capacity of water to move oil, in simple words. So if we want to increase the mobility of oil, we can diminish water mobility. Okay, so to affect water mobility, we have to act in water permeability and or water viscosity. So if we increment both, this factor will be lower and we will move more oil. Okay, so this is with math and chemistry. So why does polymer affect these two factors? Well, viscosity, because polymer in water increases the water viscosity. That's pretty chemical. And then the permeability to water also diminishes in the reservoir, because imagine then that you have water trying to get through a sponge. It will get, let's say, easy. But if that water is more viscous, it will be less simple to get in that sponge. So we will diminish our permeability in of water, okay, through the rock. Also, polymer absorbs a bit in the rock, so permeability diminishes, and the swap is way more efficient. Another good thing about polymer flooding, maybe you've heard of it, maybe not. Just for those who don't know and may have this, maybe you question, you have this question of, hey, but don't I have, maybe I have a chance of plugging my reservoir? And the answer is no, I need a good design, but risks are very limited. Basically, if I can inject water, it's almost 90% sure that you can inject polymer too. You just need a good design and know your reservoir. So just a quick look on polymer flooding history, how we've evolved in the last 50 years. First, we have a few injections in the US in the 70s, and now, after a larger success in China and many countries, we have more than 300 projects all around the world right now. Why did we have a larger success? Why did we evolve? Because we increased our application envelope. This is application envelope. I mean, where the polymer flooding can be implemented. In the 70s, polymer flooding could be implemented only in certain conditions of temperature, permeability, depth of the well, oil viscosity, and we have in the last few years increased that envelope scope because envelope application because we have developed better chemistry polymers that can stand and cope harder conditions. So now it's almost possible to implement polymer flooding in every field. So what are polymers? You may have heard this word before. It's basically repeated units of the same monomer. So we're having these monomers in chains, long chains, with a high molecular weight. And for EOR, we use acrylamide-based polymers, not just any polymers. And the average molecular weights are between 3 and 35 million Daltons. That's a lot. And that molecular weight will give us more or less viscosity. We usually use anionic to minimize the absorption in reservoirs. And this is an example of how an anionic polyacrylamide looks like when we join, let's say, acrylamide and acrylic acid, for those who like chemistry. The good thing, the important thing about polymers, I mean, why we use polymers and not something else? Because we cared about this property, which is non-Newtonian fluids. Water. If maybe you've heard that in some physical class. If we have Newtonian or non-Newtonian fluids, they behave differently. If we apply different shear rates are like efforts in a fluid, the viscosity may change or not. In water, for example, doesn't matter the strength I apply to water, it will always be the same viscosity. But with polymers, we have a decreasing in viscosity at higher shear rates. So if we implement more strength in a polymer, it will diminish the viscosity. So this is a particular thing about polymers. They're called pseudoplastic fluids or shear thinning. You may have heard any of those concepts. And I'll show you now why we can tell visually that they're pseudoplastic, because I have polymer here. Okay, so let's get a bit more visual. Polymer can be in two different forms for EOR, which are powder and emulsion. The main difference is, well, of course, one of them is solid, the other one is liquid, but the solid is 90% of polymer, let's say active content, because we have 10% of turbidity. So this is how powder looks like. I'll give it to you to look then. So we have powder, which is 90% of polymer active content. And then we have emulsion, which is liquid. So emulsion is 30% active content. And you will say, hey, well, why should I take emulsion if powder has more active content? Well, it depends on each case which one is better for application. Okay, I'll tell you now. So main differences is active content, form, and how we transfer it. The emulsion can be pumped and the powder has to be hydrated. We cannot inject powder like that. We need to inject a fluid, so we need to hydrate it first. But the good thing is that we will diminish OPEX because we won't be transporting so many non-active content. So we use powder mostly for EOR when we are onshore. Offshore, we use emulsion. Powder requires a preparation skid to be implemented. What I was telling you, we need to hydrate the polymer. And for emulsion, we have a quick direct injection, and we don't need a maturation tank. That I'll show you now what that is. So, in general, in both cases, we have a collapsed polyacrylamide. Well, this is mostly in powder, but we have a collapsed polyacrylamide molecule in solid state. And then when we put it in a good solvent, this collapsed polymer will open up. These chains will open up and will generate this viscosity in water. But we need time to hydrate the polymer and let it open up. And if we don't use a good solvent, like ethanol, then that chains won't open up and we won't generate viscosity. Okay, so it's not only about the molecular weight, it's also about the solvent. They're basically preparated for water, but the water can be better or worse, the water quality. So that's what I mean about water quality and viscosity development. The lower the salinity, the better viscosity, because the polymer is anionic, and when I put it in water, the chains open up and we generate good viscosity. But if we have many salts, like we have cations, like sodium, potassium, calcium, magnesium, then we make these chains, these charges to attract, and the polymer chains roll in again. So we lose viscosity, basically. That's why we need, every time, more developed technologies in polymers so that they can stand more salty waters. Okay. So basically, for field application, we need to know these parameters, and then we will choose a specific polymer design for my specific reservoir. Okay. So application of the polymer. If we use powder, as I mentioned before, that we need a maturation tank. This is real life. So in the lab, we will hydrate the powder in an overhead stirrer, magnetic stirrer. In real life, we have these polymer injection units, which they can be moved from one place to other. And in these injection units, we have the powder stored in a silo, in a hopper, and we hydrate it in something we call PSU, which is polymer slicing unit. Polymer slicing unit allows the polymer to pre-hydrate with the water, and then this pre-hydrated solution goes to a maturation tank, which has a certain residence time and allows the polymer to fully hydrate and develop viscosity. Then, when we have this matured solution, we dilute it with water, we mix it, and then we inject it as a diluted final solution. So, what does polymer look like? I'll show you. This looks like water, right? But polymer behaves sometimes as solid, so it will have some resistance to fluid. So this is what our solution looks like, a hydrated polymer solution. Okay. So this is what tells us that this is a pseudoplastic, because sometimes it behaves as a solid and sometimes as a liquid. It wants to move, but it has some resistance, like solids. Okay. I'll let you take a picture there. And so we have this property of viscosity. How much polymer do you think we have in that solution? Just guess, like in grams per liter, ppm, percentage. What would you say? Percentage, number. Any number? What? 5? What, anyone else? 30? Well, it has 1%. 1%. So it's just 10,000 ppm. It's one gram of polymer. 1 gram of polymer in 10 grams, sorry, of polymers in 1 liter. So it's very little amount. So you can guess that the density of polymer will be almost the same as water, but it will have different viscosity. Okay. So this is what our solution looks like. It's a high concentrated solution, but we don't use this one for injection. We use a diluted solution. That's why from the moderation tank, we obtain something like this, and then we dilute it with water. We make it pass through a static mixer, and then we inject it as a diluted solution. And in general, we inject, the projects I've been, from 300 ppm to 5,000 ppm, but still not big amounts. So yeah, we can generate viscosity with very little polymer. And also, we will have to inject a higher concentration if our water is worse. Let's say if it's more salty, I will need more polymer to achieve a certain viscosity. Okay. So how do I inject emulsion on the other side? I don't need all that moderation tank, PSU. I'll just inject it in with a pump and dilute it with water. Static mixer, injection. Okay, so we save the moderation tank step. So any questions so far? We're good? So we've seen the polymer forms, EOR, what it means, how we applicate it at field. What happens in Argentina? I'll give you a quick summary of Argentina for those who don't know our reserves. We have 5 productive basins, but 2 main basins, which are Neuquén Basin and Golfo San Jorge Basin. Neuquén Basin is this one. You may have heard of Vaca Muerta, maybe, or it's the second non-conventional gas reservoir, the second largest non-conventional gas reservoir. So it's pretty famous lately. But EOR, so far, we use it just for conventional reservoirs. So we have the most activity. The 90% of the country's verified reserves come from Neuquén and Golfo San Jorge basins. So we are going to focus for sure on these 2 basins. And the particular thing about these 2 basins is that they have a large amount of mature fields. Mature fields are fields that have been producing for many years by water flooding or secondary recovery, and we need to increment our oil production. So we are going to our EOR resources, and one of them is, of course, polymer flooding. So in the literature, we can find that recovery factor is lower than 35% in these mature fields. 12% comes from primary production, 5 to 7% more from secondary production, and about 40% of the wells are active because we have marginal operation condition and high operative costs. What does that mean? If the field is very mature and is not producing as much as they want, then it's, let's say, more expensive to keep it functioning than shut it off. Okay, so we just have few active wells. So, but if we have a recovery factor lower than 35%, I would say my first thought is, hey, I can recover more, probably. I mean, we have more oil there. So, many documented projects in Argentina proved that polymer flooding can increment from 8 to 18% original oil in place production. Okay, so it's a very interesting tool for mature fields. Okay. In Argentina, we've been implementing tertiary recovery projects since 2009, more than 20 years. We have several companies leading these efforts on EOR. These are the different EOR projects, not only polymer flooding. You can, when we talk about EOR, we also talk about gels, water shut off, and bright water, not only polymer flooding. Argentina is the country with the greatest development in polymer flooding in the region because we have many projects ongoing. So this is a good picture of our situation in the last few years. These are the incremental barrels per day that we got from EOR production. Okay, so when we started to implement EOR techniques in 2009, we incremented more than 1,000 barrels per day the production. These are different fields, the colors are different fields. And this is where YPF, which is one of the biggest oil and gas companies in Argentina, started the massification of polymer flooding. What I mean by massification, I mean we stopped injecting 10 wells and now we're injecting 100. Okay, so when we massified these projects, we saw 99,000 barrels per day of incremental oil production. So this is a documented successful. We have the data here if you want to read a bit more. And since this is very, well, when I see this graph, I say, all right, so we keep improving oil and gas production. How do we optimize this process? How do I know if a polymer flooding is well applied? Well, there's an interesting case in Manantiales Ver, a YPF company in Argentina, which optimized polymer flooding. They created some kind of a circular economy model in which they didn't do what other companies did. They didn't just put the injection plant here and let it inject for 10 years. They try to optimize where they inject and they move the plant when they stop seeing a good cost balance. Okay, so what they do is, well, this is a 3D model of a field. You can see in blue water, oil in green, and gas in red. So they find this sweet spot. They call these sweet spots. So the sweet spots are areas with most oil in place. So they say, all right, so let's inject polymer here. Let's try to produce this oil. Then they detected many sweet spots and they just put the plant's polymer injection units in those sweet spots. Then they see how much they recover of oil, how the water cut decrease. And then after a few years, they analyze if their costs are still in a good condition. I mean, if it's still worth to inject in that area, or they should change the plant location. So if they decide they should, they rotate them in a new place. And they run again this 3D modeling. Okay. So what have they found? Recovery factor with water flooding, gray lines, up to 20%. Recovery factor with polymer flying up to 60%. Okay, so they even triple their oil recovery factor. So this is a good strategy, like for reducing costs, mitigate risks, be flexible, being able to scale our 3D modeling. What they also did was to minimize water cut. If we produce more oil, we have less water to treat. So this is a good thing in an environmental, sustainable way. Okay? If I have to treat less water, then I use less energy. I have less carbon dioxide emissions. Okay, so this is a nice case of carbon footprint reduction. If I decrease my water cut per barrel produced, then I'm reducing carbon dioxide emissions. So that all being said, the main question I asked myself is, all right, so why, if we're in an energy transition stage, why are we keep putting efforts in oil and gas production? Why don't we just invest in other cleaner energy sources? Why do we do that? Well, the answer is our metrics of energy balance. According to many different sources of investigation, for 2045, 2050, we will still have a huge amount of oil and gas dependency. I mean, oil and gas remains being one of the sources in many scenarios, but not because we love oil and gas. It's because we need oil and gas for this transition. It won't be an overnight change. So how do we do to still producing oil, but decreasing our carbon footprint, because it's the main target of renewable energies and energy transition? Well, last example, the previous example I showed you is a good case. I mean, well, we need to keep producing oil while we migrate to cleaner sources, but in the meantime, we can reduce carbon footprint. Reduce per barrel of oil produced. Okay, so in comparison to the previous ways of producing oil. So some facts. I'm not gonna say we have the cleanest way of oil production, but these are actually environmental facts that shows that polymer flying reduce carbon footprint and, let's say, carbon dioxide emissions in comparison to water flying. This is our current situation. This is what we are going to, where we're heading. I mean, polymer flying. So if we inject these barrels of water flying and these barrels of polymer, then we will produce with water 1 barrel of oil. With polymer, let's say 3. This is a typical example. Of course, it can be more, it can be less. So how much do I have to inject and how much do I produce per barrel of oil? Okay. In water, I have to inject 10 barrels to produce 1. In polymer flying, 3 and a bit of barrels. So I should inject more to get the same. Okay. How much water will I produce and have to treat? All right, so I'll produce 8 barrels, and with polymer I will produce 2 and a bit. Okay, so I will have less CO2 emissions by polymer flying. Okay, so this is the, let's say, CO2 emissions when I go to water flying and polymer flying. Water flying is not a big deal with carbon dioxide emissions if I have a good recovery factor. There's nothing wrong about injecting water if I have a good oil recovery. But if water cut increases too much, then the carbon dioxide emissions increase a lot. So I can diminish that by using polymer fly. So I don't want to go too deep in the math, but I just want you to know that exists a real calculation method to determine carbon dioxide emissions, and one of them is compare before and during polymer injection, like this point to this point. And the other one is an integral method, which is more accurate because we analyze the whole production, okay, with polymer and the one we would have had with water. Okay, just the important thing is that with polymer flying, with water flying, we increment water cut. With polymer flooding, we decrease it and then we increase it again, of course, until we find the equilibrium. We are interested in this zone. This will happen with years of polymer injection. Okay. So, math. We're engineers, so we like math, but just for you to know how to calculate total carbon dioxide emissions, the total amount of carbon dioxide emissions are the energy consumption, the energy used for polymer manufacturing, because of course we're using another additive, so we have to take care, we have to consider how much carbon dioxide I emit by producing it, okay? And then other chemicals, products that are used in water, and how much carbon dioxide they produce, okay? So this is how we calculate CO2 emissions. And energy consumption will be a summary, a sum up of many things like pumping energy, lifting energy, water treatment energy, and heater energy. This is an important term because if we require a lot of energy to treat water, and we reduce the water cut, then we will have to treat less water and we will reduce that energy. So we reduce our carbon footprint. Okay. Just one case I wanted to mention. I have a few cases in which we made the calculations of carbon dioxide reduction, the savings in each stage of the project. With water flooding, we used to produce 32.5 kilograms of carbon dioxide per barrel of oil produced. And by implementing polymer flying, we went to 5.6. Okay. Why? Because when we pump with pumping, we reduce 20% of our carbon footprint. With the PIU, the polymer injection unit, we increased it a bit because we are using energy, pumps, etc. Then by lifting, the lifting energy reduced 36% of the carbon footprint. The water treatment also decreased because we have less water for treating, well, and so on. So these cases are very interesting because in many countries, in China, Alaska, Argentina, as I told you, we see the same results. The production, the carbon dioxide emissions, the production with polymer flat and water flat, how the difference that we have, how much the water cut is reduced from 70 to 20%, so 50% less water to treat. I mean, we don't need to go deep. Just want you to have that data in mind. This is another case by the integral method, also from 7 to 2.1, sorry. So we have a lot of savings in carbon dioxide per barrel of oil. Okay. Well, this is interesting. It's a summary of all literature that we have so far. The reduction in water cut, how the percentage of water cut reduction, like 60% to 80%. I mean, we have a lot of water reduction, and the reduction in carbon footprint, higher amounts of yours. it's hard to understand because it's like the increment of reduction, but it's a very interesting analysis. So we have a lot of sources that allow us to say this stuff. That really works. We have good savings. So we have this. We've seen this before. So with polymer flooding, we reduce our carbon dioxide emissions. With polymer flooding, at first we increase it until we see the response in the reservoir, until we have this incremental oil production, which is not like instantaneous. But we know that after a while we have this reduction in carbon footprint. And then the question is, all right, so we reduce the carbon footprint by injecting polymer, and what are the next steps? Optimization, moving from water to polymer. Well, we have another step, which is using eco-PAM polymers, biosourced raw materials polymers. Okay, so reducing the carbon footprint in polymer production. Okay. What do I mean about that? When we produce polymer, we use acrylamide and acrylic acid, and acrylamide comes from acrylonitrile, which comes from propylene, let's say. So propylene can come from crude oil, let's say non-renewable energy sources, or cleaner like biomass. So the proposal is to generate a good handprint by using renewable biosource to generate the propylene and acrylonitrile and acrylamide for polymer production. Okay. So this is another way of decreasing carbon dioxide emissions. So we can go from a zero emissions, which means that we go, we can have a full bio-based origin, we can have a full fossil raw material, or we can have a combination of both, which is more, let's say, achievable. Okay. So we generate zero carbon footprint by using 70% of biosource raw material. We don't need to replace all of it to generate 0% of emissions. Okay, so this is our next step as SNF. And finally, some wrap-up comments. I don't know if I'm okay. So some wrap-up comments. We know that today's policies promote alternative sources as a way of generating energy, but we also know that this shift won't happen overnight. So we need a slow transition from fuel sources to renewable sources, and for that we need oil. So we need to find cleaner and more efficient hydrocarbon production methods. Okay, so we need to, in the meantime, reduce carbon footprint in the way we produce oil. So polymer flooding is a good technique to do that. We average reduce 74% of injected water, 86% produced water, 70% of carbon dioxide emissions. So we have a win-win in here. And also to know that Argentina and America, South America in general, are good examples of this role we have in transition to more renewable energies. So I think that's it for today. Thank you. Thank you very much. So time for questions.
Sim, sim. Tem dele que mostra o equipamento funcionando através da escola. There's two movies you sent to them.
Yeah.
It shows the equipment working.
Okay, hold it. Okay, so we have two videos. technical issues. So we see the videos and then we go to the questions. Okay.
The world's population steadily grows. Land use becomes more developed and urbanized. At the same time, the demand for natural resources increases. We must preserve these supplies that are so vital for life, especially water. SNF offers solutions to water reuse and recycling. SNF is the leading global manufacturer of water-soluble polymers, providing effective solutions to the preservation of valuable natural resources in all aspects of our lives. Every year, SNF manufactures over 1 million metric tons of polyacrylamide-based products, while investing 2% of sales in research and development to continuously create new products with improved performance to treat the world's waters. SNF's core businesses are all linked to water. The production of drinking water, the treatment of municipal and industrial wastewater, water recycling and mining, oil production and enhanced oil recovery, agriculture, paper, textiles, construction, and personal care. SNF specializes in water chemistry. Our products are applied everywhere water is used, recycled, preserved, improved, reused, and modified. SNF, preserving natural resources with the environment and future in mind.
Okay, so that was a bit of publicity of SNF. For those
SNF, for easy, cost-efficient, and sustainable EOR solutions.
Sorry, just for you to know that we sell polyacrylamide, which has many uses. One of them is EOR application, the one I explained, but we also use polymers for different industries like paper, water treatment. It's not just EOR. In Argentina, we mostly focus on EOR, but it's not the same case in all the world. So just for you to know, but it's basically polyacrylamide products, okay, with some variations, but basically polyacrylamide. Yeah.
SNF, for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process, from assisting screening and reservoir studies, polymer logistics, to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. Polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.
So you could see the polymer injection units, the modular plants I talked about, and that we need a maturation tank in the case of powder. That was visual, and the way that we swept oil with water that generated canalization, it wasn't very efficient, but with polymer we can sweep all the reservoir. Okay? So thanks for the video. And well, questions? Or you understood everything and you didn't understand anything? Please. Yeah. ¿Va bien? ¿Hay preguntas?
We have some questions.
I can have another.
Thank you for your nice presentation. It was really interesting result. So I have a question about in your video, and you talk about the lifting, and it has a really large drop in CO2 decreasing trend. So can you describe more about that? How is it decreasing? So the lifting process?
Yeah, because we are analyzing barrels per barrel of oil. So if we need to treat less water, we need to lift less water. It's basically that. I mean, we're reducing our water treatment by. You have the pumping energy that you would use for water treatment, and you are not because you have less water, and the lifting energy. So when we reduce water cut, we reduce both. You know that. Maybe I'm not understanding. Tell me.
Can you elaborate more? I mean, what do you exactly mean by lifting? Do you mean that the water that you get from the sources that you want to make the treatment, or it's another meaning of this?
Hold on. I'll try to find a way they work. I don't find the word to describe what I want.
Because you produce the reservoir. So you don't have to treat that.
Yeah. What are saying? Sorry. I don't know how. I mean, when it's all about like mass balance, it's the same as with regular water injection. I mean, when you inject water, you would have to lift from your water facilities, let's say 10 barrels, and now you would have to lift 7. So that's how it decreases.
Treatment.
You will treat less water per barrel of oil produced. So yeah, it's like they come hand by hand, lifting and pumping. But we can go deeper on that topic. I have the calculations, but it's about the flow rate. I mean, you need less to produce the same.
Okay, Thank you.
No, it's fine. We can talk about it more later, but it's basically that for the same amount of oil you will produce, you will require less facilities, less energy in everything. So lifting is one of them.
Good afternoon. Thank you for the presentation. I have a question. How will these polymers behave in contact with CO2? For example, could be used in a process like water alternate gas to improve the sweet efficiency of the water used together with the CO2?
That's a good
Is it
question.
not possible?
It's a good. Yeah, it's a good question. We don't use it now because there's something called chemical degradation. If you have an oxidant like CO2 or oxygen, dissolved oxygen, you will, along with bacteria or contaminants like iron, H2S, and oxygen or carbon dioxide, you could generate the proper medium for polymer degradation, chemical degradation. So they shouldn't go together. I mean, in fact they try to avoid oxygen presence in the water. So we would avoid the same way carbon dioxide. I mean, it won't be good, mainly if you have contaminants in the water. Because I haven't mentioned it, but we use produced water. We don't use, in some cases, 1% they use river water. But in general, they use the produced water from secondary recovery. So if that water is not very clean and it has contaminants even after treatment, and you have polymer and oxygen or carbon dioxide or any oxidant, then you will have the proper media for polymer degradation and you will lose viscosity. So it wouldn't be a good scenario for polymer flying.
Yeah. In the YouTube, we have that question. I don't know if you can see what type of polymers the most used.
In Argentina, the most used polymer, thank you, Jose Maria. The most used polymer is regular copolymer, anionic, flow-com. We are starting to use flow-com products which are more resistant to salinity and temperature, I mean for harder conditions, but we are starting to implement them. When I mean these kind of technologies require a group of ATBs, which is terbutyl, like a huge molecule that stabilizes the polymer and allows it to be more resistant in worse conditions. We're starting to use those polymers in Argentina, but still a great percentage of the polymers are regular copolymers, high molecular weight.
5150?
Is 3630.
3630.
Yeah, flow-com 3630. I didn't say the number because maybe you didn't know it, but yeah, it's the sold out in Argentina.
We have another from US Nest, right?
No, we just inject synthetic polymers like polyacrylamide. No. How do fluctuations in oil prices and market conditions impact the feasibility of the implementation of polymer injection projects in Argentina? Well, polymer project can go from cost-effective to non-feasible in 1 minute. One of those factors is oil price. So yeah, if oil price lowers, then I can invest less money in our recovery techniques. So it would affect polymer injection projects. They can stop being rentable, and maybe they could stop injection. Yeah, for sure.
How much is the ton of propane 3630. Do you know the cost?
I would say 300 tons a day, if I'm not mistaken. 300 tons a day. The cost, $3 a kilogram. Depends. Yeah.
$3 per
3,
kilo.
3.5, 2.8, depends. Yeah, I'm not very into the costs. Fortunately, I'm on technical side, but it's an important question. Yeah, for sure.
Argentina is the most fields are onshore, right?
Yeah, we don't have offshore.
Okay. So
It's a legal battle.
founder at it.
But we are injecting emulsion offshore in Brazil, in El Puerto. So
In Peregrine, right?
yeah. So
And then is emulsion. Are you using there?
offshore we use emulsion always.
And do you can you say the concentration?
I couldn't say the concentration because that's like barrels per day. I don't like that unit, but I can say that, like, they have a target viscosity, and when they have a target viscosity, they calculate how much polymer concentration they need for that water. Okay, so maybe with your water you need 5,000 ppm. With mine, I need 1,000. Okay, so it can be different. They have a target of 20 centiwatts, 30, but also since polymers are shear rate dependent, we don't know their target. We don't know what shear rate has that target. Okay, so it could be 20 centiwatts at 7 seconds or at 50 seconds, reciprocal seconds. Okay, so we don't know that exactly, but they try to make the calculation to reduce mobility ratio in a cost-effective way.
Where the tests are being conducted on polymer for Peregrine?
For now in France, but we are starting to take some of that because in Argentina we're starting to increment our services for Latin America, but still Brazil is not.
I mean, yes.
We've received some water samples.
Yeah, but we did, but we don't know what they do with the knowledge we provide. You know, we don't have feedback.
I would guess SNF France, so it's our airport headquarters.
I did a lot of that.
Yeah, you did.
Yes, I did.
Okay, we can share.
No, myself, just myself.
Your team.
Me and my students, my co-workers, we did a lot.
Okay. Good to know.
Was very fun.
Polymers are funny, especially when you have to clean them.
And
Not that easy.
I would like to congratulate because you summarize all the advantages the polymer can give for us. I defend this kind of approach a long time around.
I'm also a fun club, but
it's
fun club.
Yeah,
it's difficult to summarize all these. There are many concepts, and maybe if you're not familiar to them, it's hard to understand. It looks like we want to sell something always, but it really has a lot of advantages and also environmental advantages.
What amazing.
Thank you. Thank you very much. So, any other questions?
Thank you for coming.
Thank you for the invitation.
We really appreciate your participation, your event. This is for you.
Muchas gracias. Gracias. Muchas gracias. I'll take the water. If you want to come and see the polymer aspect or touch it.